So, if you've been keeping an eye on quantum computing, waiting for those big theoretical promises to actually, well, materialize on real machines, get ready because today we're diving into something that, honestly, a lot of folks are calling the moment, the foundational shift. We're talking about researchers announcing they've achieved an unconditional exponential speedup, and crucially, they did it using actual quantum hardware. This isn't just theory anymore. It feels like it shifts the whole game.
Yeah, absolutely. I mean, for the longest time, quantum computers held out this incredible promise, right? This is immense power. But there's always been this huge barrier, this
Yeah.
elephant in the room, noise.
Yeah.
Those tiny errors, the decoherence that just wreaks havoc on quantum states, especially as you try to scale up. So this deep dive, it's really about how a team might have just found a way to seriously tackle that fundamental problem.
Okay, let's unpack this. Our mission today is to figure out exactly how these researchers pulled off this unconditional exponential speedup on real quantum processors. What do those words really mean in this context? And, why is everyone saying this is such a monumental milestone? We're mainly looking at an article from SciTech Daily from July 1st, 2025. It covers research out of USC and Johns Hopkins, which was first published in Physical Review X. Pretty serious stuff. All right, so the core achievement, we've got researchers from USC Johns Hopkins led by Daniel Lidar. They used two of IBM's Eagle processors. Those are 127 Kubel machines. And what they showed was this unconditional exponential speedup, which, as you said, sounds like more than just a small step forward.
Oh, it's way more. What's fascinating here is getting what exponential speedup actually entails. We're not talking like 10 times faster or even 100 times faster. Think about it like this. You have a problem. As you make it more complex, maybe add just one more variable. The time it takes the quantum computer versus the best possible classical computer.
Yeah.
That gap roughly doubles. For every single variable you add, it's, well, LiDAR calls it the most dramatic type of speedup we expect from quantum. That kind of scaling, that's what makes quantum potentially so powerful, so different.
And the unconditional part, that sounds important too. What does that add? Because I remember past claims, they often had this sort of asterisk, right? Like, assuming we haven't found a better classical algorithm yet.
Exactly. That's the crucial difference. Unconditional means they didn't have to rely on any unproven assumptions about classical computing's limits. See, LiDAR's team, they were clever. They actually modified an algorithm specifically for a version of something called Simon's problem.
Hmm.
They set it up so the quantum computers win inherently proved the advantage without needing that assumption.
Okay, so that unconditional aspect really strengthens the claim then. It takes away that wiggle room for skepticism.
Massively, yeah. It addresses that what-if question head-on. Before, you could always argue, well, maybe someone will find a faster classical method tomorrow.
Hmm.
Here, they engineered the test to basically say, nope, based on the structure of this problem, the quantum approach is fundamentally faster. It's about computational superiority baked in.
Got it. And the test itself was Simon's problem? You said it's like a guessing game?
Sort of, yeah. Think of it like a guess the pattern puzzle. You're trying to figure out a secret pattern represented by a binary number. Its specific mathematical structure is just perfectly suited for quantum algorithms. It lets them use superposition to find hidden features, these periods, exponentially faster than any classical method could. The game involves querying an oracle, like asking questions about the secret. Once you find two different inputs that give the same output, you can figure out the secret and the quantum way of playing. Exponentially fewer questions needed.
Okay. And why is this specific problem, Simon's problem, so significant?
Well, if we connect this to the bigger picture, Simon's problem is seen as the forerunner, mathematically speaking, to Shor's algorithm. And Shor's algorithm, well, that's the famous one, the one that could potentially break a lot of the encryption we use today. The possibility of Shor's is really what kicked off the whole quantum computing race decades ago. So demonstrating this kind of speed up on Simon's problem on real hardware, it's like proving the core engine works, even if you're just using it for this specific, though foundational, task right now.
Right. But okay, that brings us back to the big hurdle you mentioned earlier, noise. If noise has always been the kryptonite for quantum computers, how on earth did they manage this exponential speed up despite that? Here's where it gets really interesting.
It really is. Fatheraporn Sinkanipa, who was the first author on the paper, said the key was, and I like this phrase, squeezing every ounce of performance from the hardware. They basically used the toolkit, what they called 4 tricks, these really smart methods to fight back against the noise and keep things on track.
4 tricks. Okay, what were they?
Right, so first, they limited the data input. They restricted the number of possible secret numbers in their version of Simon's problem. Fewer possibilities meant fewer quantum logic operations were needed overall. And fewer operations mean fewer chances for noise to creep in and cause errors. Simple, but effective.
Makes sense. Reduce the workload, reduce the errors. What was trick number 2?
Second was transpilation. You can think of it like optimizing code for a specific computer chip. They compressed the sequence of quantum logic operations needed, making the quantum circuit as efficient as possible, specifically for those IBM Eagle processors, squeezing out redundancy.
Okay, optimizing the instructions.
Yeah.
And the third?
Third, and this one sounds like it was maybe the most impactful, was dynamical decoupling. This involves hitting the qubits with these carefully timed sequences of microwave pulses. The goal is to sort of actively disconnect the qubits from the noisy environment around them, shield them while they're doing their calculations.
Yeah.
The researchers themselves said this trick had the most dramatic impact on getting the speed up to actually show up.
Wow, so actively fighting the noise in real time with pulses. And the fourth trick?
The fourth was measurement error mitigation. So even after dynamical decoupling, some errors still happen, especially when you try to read the final state of the qubits. It's not a perfect process. This last step involved techniques to statistically correct for those measurement imperfections, sort of cleaning up the final answer.
So it wasn't just one thing, was it? It was this combination: constraining the problem, optimizing the code, actively shielding the qubits, and then cleaning up the results. It's quite an effort.
Exactly. It's a suite of techniques working together, really pushing the current hardware to its absolute limit and managing the noise just enough to see that underlying quantum advantage shine through.
Daniel Ladar, the lead researcher, put it pretty strongly. He said, the quantum computing community is showing how quantum processors are beginning to outperform their classical counterparts in targeted tasks and are stepping into a territory classical computing simply can't reach. That sounds definitive.
It really does. And he doubles down on that, saying this result, quote, shows that already today's quantum computers firmly lie on the side of a scaling quantum advantage. And crucially, because it's unconditional, he adds that this advantage is becoming increasingly difficult to dispute. It's moving from theory to something you can actually point to on a machine, which is huge.
But then there's the practical side. I mean,
Yeah.
okay, they won a guessing game, essentially. How big of a caveat is that?
That's the critical nuance, yeah. And Lidar himself is very clear about this. He cautions, quote, this result doesn't have practical applications beyond winning guessing games.
Right. So proving the principle is one thing, but using it for, say, drug discovery or material science is another.
Exactly. The demonstration of the exponential speedup principle is profound. That's the milestone. But this specific setup still used an oracle, that pre-programmed element, that kind of knows the answer structure for Simon's problem. For real-world stuff, we need to show these kinds of speedups on problems without oracles, problems where we genuinely don't know the answer beforehand. And, of course, we still need massive progress in reducing noise and building much larger, more stable quantum computers. Scaling up from 127 qubits is still a huge challenge.
So important caveats remain.
Definitely. And this is the key takeaway, even with those caveats, that fundamental on-paper promise of quantum computers delivering exponential speedups, that's now been shown firmly.
Yeah.
On actual hardware, that's a barrier that's been crossed.
Okay, so summing it up, we've now seen undeniable proof on real machines that quantum computers can exponentially outperform classical ones for certain tasks. It might be a specific task for now, but the principle is demonstrated. It feels like a foundational brick has been laid.
Absolutely. I think this really shifts the whole conversation. It moves it away from if quantum advantage is possible to how and when we can harness it for practical problems. The potential is now demonstrably real. So for you, listening to this, maybe think about it this way. Now that we know this kind of speedup is real, what kinds of problems maybe in science or finance or AI might finally become solvable once we move beyond these guessing games?
That's the big question, isn't it? What happens when this power gets unlocked for real-world challenges? It really makes you think about the long-term implications. What could that future look like?